Hello everybody, this is Dr. Hussein in Introduction to Digital System. Our topic today is how we minimizing using Karnaugh map. Okay, so the overview of this topic is using Karnaugh map as an alternative approach to represent Boolean function. We represent the function using truth table, using block diagrams, and we use Boolean to simplify to get the minimum function presentation. Now we will see how we use a Karnaugh map. Okay, also Karnaugh map used to minimize rather than Boolean. We properties, Boolean algebra properties, we use Karnaugh map to simplify. And it's used easy to convert or simplify and convert or minimize sum of product presentation. Okay, we will see that there is simple rules used to perform the minimization, and this lead to minimize the sum of products. Okay, now Karnaugh map. Now Karnaugh map, we represent the truth table. Example, if you see here this expression, the function f, okay, expressed by x dash y x double plus x double dash y double dash, which is sum of products. Okay, this is the truth table given to you, as you can see here, x, y, and the output. We can represent using Karnaugh map by squares. You can see here, okay, this is square where you can see, by the way, we have two variables, so we have 2 to the power 2, 4 squares. Okay, if it is a 3, 8, it will be 8 squares. Now here 4 squares, as you can see. Now y, this side represent the y, and this side represent the x. And as you know, y or x, each one of them either 0 or 1. So we write here 0, 1, 0, 1. Now you can see here when x and y 0, f will be 1. You see here, x 0, y 0, so we put 1 here. And here, when x is 0, y is 1, x is 0, y is 1, we put 1 here. Otherwise, it will be 0. So we simplify the truth table here in this squares. You may ask, okay, what is the benefit from this? Later on, we will see how we minimize and simplify. To simplify, use Boolean algebra, let me say properties, distributive or De Morgan theorem, or other properties, associative property, and other properties. It depends on our experience. We solve more problems similar to math. We get the experience to solve and simplify. But using Karnaugh map make my task easy, as I will show you later. Okay. Now, as you can see here, Karnaugh map. Okay. You see here, this is another expression. Without looking to the function, here a b dash. It means when a1, b dash 0, and when a0, because dash here, a dash, it means 1, it will give 1, and here 1, we have 1. Let me see. This is a, and this is b. 0, 1, 0, 1. Okay. When a is 1, here a is 1, and b is 0, here b is 0, so we have 1. And here, when a dash is 0, here is 0, and b is 1, here b is 1, we have also 1. You see how I fold the squares? Okay, another expression. Okay, the difference between this expression and the previous one is we have AB. AB, it means when A1 and B1, we have 1, right? This is A1 and this is B1. They are intersecting here, so we have 1. Okay. Now, if we have 3 variables, you can see these are the 3 variables. Let me say from the truth table. This is the truth table. This is the first one, the second one, the third one, fourth, 5, 6, 6. And you can see here the expression, we have 6 different combination of ABC. Now when I put the square, by the way, we have 3 variables, so 2 to the power 3 is 8 squares. When I come, let me take the first one, this one. This one tell me that when A is 0, B is 0, C is 1, I have output which is 1. So I can say it is A dash B dash and C, because when 0 here it will give 1, when 0 here it give 1, then here 1 is 1, so at the end we have 1. So just let do this. By the way, here I put A on the left side and on the top BC. You may say, can I put AB on the lower side, C on the, yeah, you can do it. Have a look here. For A, for the first one, A is 0, this, it means this one. It means this row. In general, this row. B dash, it means B 0 1, B and C 0 1. Where is 0 1? This 0 1. Then this is 0 1. Then I can put 1 here. Now let's take the last one. All of them are 1. A is 1. It means this row, and all of them this is 1 1. So here I have 1. Let's take another one. This one. Okay, 1 A is 1. This is A is 1. And BC 0 0, BC 0 0, then this is the part, and I put them here. It's very easy. Okay, so the rules for Carnot map, let me list them for you. Now it's clear, I think, but it's good to summarize what we discussed now till now. We can reduce function by circulating once in the Carnot map. Later we will see how we circulate them. Each circle represents min-term reduction, and as you can see from the truth table, if we have 8, let me say option from M0 to M7, then we have min-term, then we distribute them in these squares. Following circles, circling, we can reduce, minimize, and or form, okay, as I will explain in the next few slides. Rules to be considered here when we simplify and minimize using Carnot map is every cell containing one must be included at least one. You should not ignore any one of them. All of them should appear in our solution. The largest possible power of two rectangle must be enclosed, as I will explain in the next slide, and the ones must be enclosed in the smallest possible number of rectangles. This is the meaning of simplifying or minimizing. Now have a look here. Okay, see this expression. Just a minute. Here in this expression, in the previous slide I showed this expression. I want to simplify it. So the normal way we simplify it without Carnot map is we use the properties. I mean, we add, we take common, we simplify, we use De Morgan theorem and so on. But here, using Carnot map, the situation is easy. Have a look here. These two ones are adjacent, so I circulate them. Okay, and now as you can see, these also I circulate them because they are adjacent. Now I start looking, how can I implement this? As example, how this circle, what will implement them? You will say, okay, A will implement them. See here, for this circle, what is, you tell me A is 1, then output is 1. And this circle, B is 1, output is 1. See here. Now this is 3 variables, A, B, C, and this is the expression. I discussed this in the previous slide, but see how I will simplify. If I circulate all these ones, you will directly say, okay, when we have A, we can get these ones. Okay, what about these ones? These ones, how we can get them? Just a minute. A sometimes 0, sometimes 1, it's changeable, so we can not include it in the expression. But these ones can be achieved by having B dash, the inverse, times C. Easy? Okay, let's go to the next one. This one also. Okay, this can be achieved by B C dash, as you can see here. You see, I simplify this expression, okay, with many items, almost 6 items, into these simple items using kernel, and it's directly coming here. You can see how easy is this. Now more examples here. See this. Already I put kernel map for some examples. See these ones. When I circulate them, they are adjacent, and ones 0, 1 I cannot include A, but 0, 0 I can include B and C. I will say this is B dash C dash, or in this way, in this representation. What about this one here? This one here. You see here, A is 1 in both of them, in both of these. You can see, so we write A. Okay, here B, C. C, as you can see, sometimes 0, sometimes 1, I cannot include it. But B is 0, 0, so I can include B dash, as you can see here. Have a look at this. These fours, okay? These fours, all of them adjacent. See, 0, 1 for A, we cannot include A. See here, C sometimes 0, sometimes 1, we cannot include it. But B is 0, 0. So all of these ones happened when we have B dash. Whenever we have B dash, as soon as we have 0 for B, directly we get 1, and it's represented very easily. And the same thing for others. I advise you to have a look at the other examples. It's already solved, but check them, how we come up with. Now, numbering scheme based on a gray code. You remember gray code, we discussed it in one of the topics in the previous one. Okay, can be followed the same way. Have a look here. Have a look here. See this. Let me say, example, truth kernel map given to you, and ones here. Now I will start circulating the first one. These two ones are adjacent. But have a look here. For B, it's 1 all the time, so we can write B, as you can see here. We cannot write C, because C sometimes 1, sometimes 0. For A, here, it is 1 in both of them, so we can write A. So you can see the output is A, B for this part, for this circle. Now let's come to these ones from the top, and these ones from the bottom. They are adjacent because we can close them. Okay, the same thing as example here. If these are ones, we can circulate there with these ones. Okay, now have a look here. Now in this row 0, 0, in this row we have 1, 0, so directly we will say B is not included, but C is included as C dash. And here in the top, A cannot include it because 0, 1, and as we mentioned, B cannot include it. Okay, or you can see here, BC can include it if we take only this part, but because we take the two parts, we need to include it. Or let me say it in another way. This one here, okay, represented by B C dash, and this one here represented by B dash C dash. If I add them together, I will come up with this circle and this circle, which is represented here by this one. We can use the let me say the properties by taking distributive property, by taking C dash as a common. What is left, B dash plus B, we simplify it to 1, and then we have C dash. But because of these two ones and these two ones are adjacent, because from the top and bottom, we look to what is the common element in all of them. 0, 1, so for A I cannot include it. 0, 1 for B I cannot include, but it seems to be that C available in both of them, C dash. So I can say directly it is C dash. You see, just have a look at adjacent ones and select the output. I leave the remaining example for you to practice. Okay. More examples are given here. You can see I will discuss this example. I will discuss this example. Have a look. We have ones here. We circulate them. You see here, I circulate this one, which give me, as you can see here, C1 in all of them, and B is 1 here and 1 here. I cannot include A because A is 0, 1. Okay, so it become BC. This is BC. See here, this one. Okay, this one is, I cannot include C because C sometimes 0, sometimes 1, but here it's AB. I include AB. I come to the last one, this one. Okay, this one, C is available, I put it, and A, you can see here, A here 1 and A here 1, so I can include A. I cannot include B because B sometimes 1, sometimes 0, so we have the third item. See how easy is this? Okay. Now, how we use Karnaugh map for the 1-bit adder? This is an adder. Okay, you can see here the input is A, B, and Cin, and the output is S and C out. And he gave you the truth table here. We want to use Karnaugh map to simplify. Now, for S, I will not have a look at S because you understand how you can find it's found from the table here, Okay, look to the ones and then write the minterm. And the same thing for C out. C out, look to the ones and find the minterms. As you can see here, these are the minterms. Now, if I want to take the long way or the ordinary or conventional method, which is using Boolean expressions and their properties, I will come and add, as example here, these expressions. I will add A, B, C, N here and here because I want to take a common factor, and then I take A dash plus A as a common, B dash plus B as a common, C dash plus C as a common, and then these give me ones, and I move through the simplification until I get the final expression BCN ACN plus AB. Now, we learned this before, but this is long and this depends on experience. And when more variables we have, more complication came in. So using Karnaugh map make my task easy. As you can see here, this is Karnaugh map from the table. You can see A represented by these 4 elements, and B by this row, and Cn by this one. Now take them 0, 0 and add them. Add C out when we have A, as example here in the red one. When A is 0, B is 1, Cn is 0, we have 0. So look at it and then distribute the zeros. I take them one by one. Okay, similar to the previous one. It's not necessary to put them to the right and the left. Okay, we can distribute them inside in this way. Okay, now how I solve them? Have a look. Circulating, as I mentioned, adjacent. I circulate this one. Okay, which tell me that when A is 1 and C is 1, we have output. So I write ACN. Easy? Okay. Circulate the other two. Here you can see here, A is 1 in both of them, and B, you see to the left, B is 1 on all of them, so I have AB in red. As you can see, I added to the expression. I go to the third one. Now here, B is 1, and C also is 1, so I added to the, so you see, I'm circulating directly. I find the minimum expression and I simplify it. Sometimes you don't have the opportunity to simplify. As example, this one here is another example for adder, and this is the truth table, and this is the Karnaugh map for us. I want to see how can I minimize. You see here I have 1, here I have 4 ones in the squares. The first one is happened when B is there. So A and C should be A dash C dash. As you can see here, A dash B C dash. I go to the second one. Here, when C is 1, there is no A, no B, so I will write A dash B dash C. Here, you can see when Cn is 1, but and B is 1, but A is not there. Okay, sorry, A also 1, as you can see here. So I put it in this way. Last one is when A is 1, but B and C dash, both of them are not there, so I put dash. Is there any way to make a reduction or minimize? No way, because there is no adjacent one. If you look, there is no adjacent one, so we cannot make any reduction. Now let me summarize what we discussed. Karnaugh map allow us to represent functions with a new notation, simple notation, minimum notation. Okay, representation allows for logic reduction. We make the logic reduction. Each square represents one min-term, and we learn how to find the min-term from the truth table, and we put them in a squares. Each circle leads to one product term. You should not ignore any ones in the Karnaugh map. You should cover them by circulating the adjacent ones. Not all functions can be reduced. Sometimes we cannot, as I show in the last example. Each circle represents an application of either distributive or complement rule, as we discussed before. Let me stop here. See you in the next topic.